Welcome back everyone to Aviatrix Deep Dive. In this session, I'll be discussing FireNet in Azure. So as a reminder, please make sure to watch the previous FireNet session marked as a prereq, which is basically mandatory for all the CSP-specific FireNet sessions where we discuss all the basics of the FireNet, including the common features across all the clouds. Now let's dive deep into the Azure FireNet. So there are two gateways which we create in the Azure Transit FireNet. So if I'm going to draw a Transit FireNet, and let's say this is the region which is capable of availability zones, then Aviatrix controller is going to deploy the Aviatrix Transit gateways per availability zone. So that becomes your transit primary, that becomes your transit HA gateway. So what happens when the Azure does not support the availability zones? So at that point, Aviatrix controller is going to create the transit FireNet gateways in availability sets automatically, so you don't have to do much. So what is going to be the size or minimum size of the Aviatrix transit FireNet gateways? It depends on your deployment. If your deployment is a standard deployment, for that, it's a B2 MS is the minimum size that we support for the transit FireNet gateways. And our recommendation is always to go with the insane mode to have this future-proof, or we also call it the high-performance encryption, or HPE. For that, the size for this gateway is going to be D3 V2. That's the minimum size. We require at least 3 interfaces on the transit FireNet gateways. Let's talk about those 3 interfaces now. So this is transit FireNet gateway. ETH0 is the interface, which is a management interface for all the internet traffic, including the controller traffic. So the controller communicates with the transit FireNet gateways on ETH0. So controller actually manages the NSG on this ETH0 as well. So if you take a look at the NSG on the ETH0, then you will see the port 443 is open from the controller IP. So it can communicate with that. And at the same time, the Azure ILB also communicates on this interface. We also allow transit VNet to transit VNet traffic. So anything which is in this transit VNet should be able to communicate with each other. There are certain other rules which are by default rules, those 65,000 and 65,001. Besides that, we also have a NAT rule. This is required for the native VNet peering. So for example, there could be some VNets which does not have Aviatrix spoke, and they want to communicate with the other spokes, and those application spokes could be with Aviatrix spoke gateways, or maybe those are native VNets. So at that point, we wanted to make sure that when traffic comes to Aviatrix transit FireNet gateways, it can send the traffic to the respective destination. So from now onwards, I'll be using the word spoke VNets. Basically, spoke VNets are those VNets where the application resides. ETH1. This is the interface where Aviatrix Transit Gateway communicates with the load balancer. And the firewalls behind the load balancer communicates directly back to the ETH1. Because of this reason, there is no NSG configured from the Aviatrix controller, which basically means all the communication is allowed, everything is allowed on this one. ETH2 is a special interface. Most of the deployments, you basically don't need it. This is for native VNG integration. Aviatrix platforms ingest all the spoke VNets where your application resides, because most of the time the deployment is a brownfield deployment. But for the transit, we require you to create the transit VNet from the Aviatrix controller. And the reason again is because we wanted to make sure that we have appropriate subnets created, route tables created, association of the route tables to the subnets are done properly, and at the same time we create the ILB for the load balancing of the firewalls too. For that purpose, we require you to create the transit VNet from the Aviatrix controller. So when you create the transit VNet from the Aviatrix controller, at that point we create 4 subnets. So the subnets will be created in the transit VNet, and it's per availability zone. So one subnet is going to be the gateway and firewall management subnet. Same thing in the second availability zone too. Let's say this is AZ1, this is AZ2. Gateway and firewall management subnet. There will be another subnet which is ingress and egress subnet for the firewalls. Same thing over here in the other availability zone too. So these are the 4 subnets that were created at the time of the transit FireNet creation. At this time, we don't create any routing table. Routing table will be created at the time of the gateway deployment. So when you deploy the Aviatrix Transit Gateway, at that time you have an option to enable the Transit FireNet functionality. And we highly recommend you to enable that, because once you create the gateway without enabling this functionality, you won't be able to do it again. So you have to delete the gateway and create it again in order to enable the Transit FireNet functionality. So a standard transit gateway or transit FireNet gateway will be deployed in this particular subnet, which is the gateway and firewall subnet, depending on the availability zone. So when you are creating the HA transit FireNet gateway, then you will be deploying it in the second availability zone. At the time of the gateway creation, which is the transit FireNet gateway creation, we also create 3 more subnets at this point. These subnets are VNG subnet. The second subnet is DMZ firewall subnet, and third subnet is DMZ firewall LAN subnet. This VNG subnet is for native VNG integration, and again, just skip this one. You don't have to worry about it because most of the deployment is without this VNG integration. DMZ firewall subnet is the subnet which is used to communicate with the ILB. So when Transit FireNet Gateway receives the traffic, then they send to the ILB in order to send the traffic for the inspection. DMZ firewall LAN subnet is responsible for the communication between the firewall and the transit FireNet gateways. So when you deploy the transit FireNet gateways with the high performance encryption enabled, and which is basically the recommended way of doing it to keep it future proof, at this time from the drop down menu you will see /26 subnets per availability zone if your region allows the availability zone. Pick that. Aviatrix controller is going to create the new subnets. So /26 subnets will be created per gateway, one for the primary, and then the second one, another /26 subnet for the HA Transit FireNet Gateway. At the same time, Aviatrix controller is going to create 3 more routing tables too. The first routing table is going to be your FireNet gateway name, and then the gateway routing table. So I'm going to write it here, gateway routing table, and here is the name of your gateway. And your firewall management subnets, these subnets are going to be associated to this particular routing table. And then the route which you will see is quad 0 will be pointing towards the internet. We wanted to make sure that the controller can communicate with the gateways too. There will be two more routing tables that Aviatrix controller is going to create. One of them is the DMZ firewall routing table, and the second one is DMZ firewall LAN routing table. So what is the entry in the DMZ firewall routing table? As I explained previously, that this is the subnet which is responsible for the communication between the Aviatrix transit FireNet and the load balancer. So once the traffic is received by the transit FireNet gateways, then we are going to send the traffic over to the load balancer. So here you will see quad 0 pointing towards the ILB. The last routing table is DMZ firewall LAN routing table. And here you will see quad 0 will be pointing towards the transit FireNet gateways ETH1 interface, because this is the routing table that is responsible for the communication between the firewall over to the transit gateway. Now when you deploy the Aviatrix transit FireNet gateways in insane mode or high performance encryption, at that point there will be one more routing table that gets created, and it will be with the transit FireNet gateway name. So that will be the gateway name, and then the controller private IP. So this would be the controller private IP, and then gateway dash public routing table. And here quad 0 will be pointing towards the internet. This routing table is also a very important routing table where we have quad 0 pointing towards the internet. It solves the problem of the split tunneling when you are sending the route from the on-prem, like a quad 0 route from the on-prem for some of your use cases. So at the time of the transit FireNet gateway, Aviatrix controller also deploys a standard load balancer or an ILB in the Aviatrix transit FireNet. Now let's talk about the supported architectures. So this is the architecture where Aviatrix spoke. Let's say this is the spoke VNet 1 or application spoke 1, spoke 2. When they wanted to communicate with each other and they also wanted to inspect the traffic of their application, the traffic actually goes through from spoke 1 to the transit FireNet and then over to the spoke 2. The traffic flow we will discuss in the next few minutes. So this architecture is a standard architecture which allows the inspection of east-west traffic, north-south traffic, and basically all the traffic coming from the on-prem as well. One more architecture that we support for those organizations and enterprises which wanted to have the separate egress from the east-west inspection. So at that point, what you have to do, you have to create one more transit, and then here you will have the Aviatrix transit FireNet gateways again, and then Azure ILB, and behind Azure ILB there will be the firewalls, next generation firewalls. Okay, so the first one becomes your east-west. The second one is for your egress. From the application spokes perspective, you have connectivity to both. But the first east-west one is responsible for the east-west traffic, which basically means there is the RFC 1918 routes are going towards the east-west, while quad 0 routes are going towards the egress FireNet. So there are two FireNet, and both spoke application VNets are connected to both east-west and egress FireNet. So this is also a supported architecture for the enterprises who wants to segregate their east-west and egress traffic inspection. A couple of things you need to make sure when you're creating this type of architecture with a dual FireNet. In this, you want to make sure you disable the traffic inspection on the egress FireNet. And at the same time, you need to enable the egress control from this egress FireNet. If you have a dual transit FireNet architecture in both multi-region or multi-cloud environment as shown here, and you would also like to provide connectivity between them, then make sure you are connecting only east-west transits via transit connectivity and filter out the default routes accordingly. Okay, consider application A wants to communicate with application B. Application A is in spoke 1, application B is in spoke 2. Application A has its routing table where Aviatrix controller is going to configure the RFC 1918 summary routes, which will be pointing towards the Aviatrix spoke. Then the step number 1 is it's going to look at that routing table and send the traffic over to the spoke. Now spoke is going to take a look at its own routing table. Just imagine this time the traffic comes to the primary spoke gateway. Now at this point, the spoke should have a route towards the spoke 2 and that route will be available in the spoke gateway routing table. And it has two paths. Either it can send the traffic over to the primary transit or HA transit. Let's say the hashing is done and then the tunnel to the primary transit is going to be selected. Now the traffic is received by the transit. What transit is going to do? At this time, transit is going to check whether the inspection policy, which is the FireNet policy, is being configured for this particular spoke. Either the source or the destination is already configured or not. Assume in this scenario that spoke A and spoke B gateways, all those gateways are under the inspection policy. So at this time, transit is going to say, okay, I do have an inspection policy. What am I going to do? I'm going to send the traffic over to the ILB. At this time, it's going to utilize the gateway firewall routing table because it has a default route, quad 0, pointing towards the ILB, and it's going to send the traffic over to the ILB. Now, ILB is going to do its magic. It's responsible for maintaining the hashing and everything. So it is going to send the traffic to one of the available targets, which in this scenario is going to be our next generation firewall. Next generation firewall is going to inspect the traffic. So let me write this thing, number 4, and this time, number 5, the traffic comes back to the firewalls, and then the firewall is going to inspect the traffic, and this time traffic is not going to go back to the ILP because firewall is going to utilize the DMZ firewall LAN routing table, which has a default route set to one of these transit gateway. Depending on the number of firewalls, the route will be created in those routing tables, and it will be load balanced between the transit primary and transit HA. So let's say in this scenario, we send the traffic back to the transit primary. So now, traffic is received by the transit gateway primary. Transit gateway primary is going to send the traffic over to the spoke 2 because that is the ultimate destination. It does has a path to this spoke 2 address space, and it could either send to the primary or secondary. Let's say it sends it over to the primary spoke gateway. From here, the spoke knows how to get to the address space of this spoke VNet. It is going to use this ETH0 and send the traffic over to the B, which is the ultimate destination. Now, destination B says, okay, everything looks good. I'm going to respond back to A. It is going to send the traffic to spoke gateway. Now a spoke gateway has again two different paths available. Either it can send to primary or HA gateway. It basically does not matter for the understanding of this traffic flow. Let's say it sends it over to the HA gateway. Now HA gateway receives the traffic, and this traffic is basically destined for the A. But since the inspection policy is configured, then the transit gateway is going to utilize again the same routing table, which is DMZ firewall routing table, where quad 0 points towards the ILB and sends the traffic over to the ILB. At this point, what ILB doing, ILB is, since it's maintaining the hashing, it knows there are 4, 5, 10 number of firewalls that are attached to me. But since I am maintaining the hashing, I'm going to send the traffic over to the firewall, which receives the initial traffic. So it is going to hash it back to this firewall. Now, firewall receives the traffic, it does its inspection, and sends the traffic again to the transit gateway using its DMZ firewall LAN routing table, pointing towards this particular transit gateway, which is a primary transit gateway for us. So that was the step number 11. Now traffic comes back to the transit FireNet, and this time, since the traffic is now destined towards a spoke A, it sends the traffic over to the spoke A, and then the spoke is going to utilize its ETH0 interface and sends the traffic back to the source, or in this scenario, the destination. So that's how the traffic flow works when the spoke A and spoke B are all Aviatrix spoke with the spoke gateways. Now let's take a look at one more scenario where spoke 1 is the Aviatrix spoke, while spoke B does not has Aviatrix spoke gateways, which basically means the native VNet peering. Alright, so in this scenario, spoke A is an Aviatrix spoke, while spoke B does not has Aviatrix spoke gateways, which basically means it is a native VNet peering and connected to the Aviatrix transit. So now, let's say B this time is communicating with A. So B is going to utilize the Aviatrix transit as an NVA, and here Aviatrix controller is going to configure the RFC 1918 summary routes and pointing towards the transit gateway. So the B is going to send the traffic over to the transit gateway. Transit gateway is going to look at the inspection policy. Either A or B or both, any of these conditions match that they are part of the inspection policy, then it's going to send the traffic over to the ILB. Again, same thing. It's going to utilize those routing tables which I discussed in the previous flow. ILB receives the traffic, sends the traffic over to the firewall. Firewall inspects it. Firewall sends the traffic back to the transit gateway. This time, the transit gateway could be the HA transit gateway. Now, HA transit gateway is going to send the traffic over to the destination A using its spoke to transit connectivity. Once the spoke receives the traffic, they will send the traffic using the ETH0 interface because that's part of the VNet address space. And the return traffic is going to follow exactly the same path too. Packet walk of egress traffic inspection is almost identical, except you need to turn on egress through firewalls feature. That will advertise quad 0 route to all the inspected application spokes. Traffic will follow this default route to get to the transit FireNet gateways. FireNet gateways will check if the inspection policy is configured for the source spoke and if it's true, gateway will redirect the traffic to the load balancer. Load balancer will perform its hashing and select a firewall for the inspection. Firewall will inspect the traffic as usual, but this time firewall will also net the traffic and use its egress interface to reach internet by using transit FireNet public firewall ingress egress subnet and system route of quad 0 that points to the internet. So this is all about when the traffic is communicating between the two different VNets. So we call it the Intra-VNET traffic inspection. So what is going to happen when you have different subnets inside the VNet and you wanted to make sure when these subnets communicate with each other, then the traffic is always inspected. So let's take a look at that. So the feature that we are going to discuss now, it's called the Intra-VNET inspection or subnet level inspection. So let's draw a VNet. So this is a VNet, and let's call it a spoke or application VNet. And its address space, let's call it 172.30.2.0/24. It has multiple subnets here. So this is your application 1. And let's call it 3-tier application. So application 1, web, subnet 1. There is another subnet. We can call it app 1, web, subnet number 2. We do have the app tier here as well. This could be app 1, app subnet 1. So this is the web tier. This one becomes your app tier. And then there is another subnet. We are calling it app 1, DB subnet 1. There are some other subnets here in this VNet. And these are not part of the 3-tier applications that we are talking about right now. In order for Aviatrix to achieve this Intra-VNET inspection or subnet level inspection, we define a new concept which is called the subnet group. So what we are going to do, we are going to group these subnets in a certain way that whenever they wanted to communicate with each other, they can communicate using the VNet routing tables. So what do I mean by that? So for example, you can place these two subnets in a subnet group, and we call it a web subnet group. SG for subnet group. This is the application subnet, so we can use a different color. And we can say this is a application subnet group, while our DB is part of a different subnet group, and we can say it's a DB SG or subnet group. While all the other subnets, which are not part of this 3-tier application, are not part of any subnet group at this point. So what this subnet group is actually doing, it's just a logical grouping of subnets and nothing much. Since this subnet group is part of only this particular VNet, they have local significance. So if you want, you can use the same name of these subnet groups for a different VNet too. So it does not go outside the boundary of the VNet. Okay, now let's go into the details. There could be some applications, and then let me actually put some subnets here. Let's say, since this is 172.30.2.0, so I'm going to use just the last octet. Let's say this first subnet is .80. The second subnet could be .96. And these are all /28s. And this guy could be /112. And this guy could be .128. So these are the subnet IP addresses scheme. Now when the applications, there are some servers, let's say they want to communicate with each other within a subnet number 1. So let's say there are some VMs in app1 web subnet 1. When they want to communicate with each other, they can just use the native VNet routing table, and then they can just communicate with each other. So they don't have to go anywhere outside. They don't have to communicate with the Aviatrix spoke gateway. By the way, let me draw a one Aviatrix spoke gateway here as well. So this is Aviatrix spoke gateway, AGW Aviatrix gateway. So what about if a VM in app1 wants to communicate with a VM in subnet number 2? Even at this time, they don't have to communicate with the spoke gateway at all, because both subnets are part of the same subnet group. So in both scenarios, whether the VMs inside the subnet wants to communicate with each other, or when VM between these two subnets wants to communicate with each other, as long as they are part of the same subnet group, they don't have to go outside and talk to the spoke gateway at all. Now, what is going to happen when web subnet group subnet is going to communicate with the app subnet group subnet, which is the app1-app-subnet number 1. From the deployment perspective, what you have to do, you have to create these subnet groups on the Aviatrix controller. When you create these subnet groups on the Aviatrix controller, at this point, we are going to create the routing tables too, like 2 routing tables per subnet group. So for web subnet group, we are going to create 1 public and 1 private routing table. So in this scenario, we will be creating a total of 6 subnet group, 6 routing tables, 2 per subnet groups. Now, when you associate these subnets to the subnet group, again from the Aviatrix controller, at that point, these subnets will be associated to the public routing table. So both these subnets, like app1 web subnet 1 and web sub 2, will be part of this public routing table. In this scenario, app security subnet group has only 1 subnet. So that subnet will be associated to its own routing table. And which routing table? Again, it's going to be a public routing table. Now, what this routing table is going to look like, it will have a route towards the, since we are talking about it's .80.96, so 172.30.80, I'm sorry, 2.80. 2.80, and then its next hop is going to be the virtual network, or VNet. Same thing with the second subnet, which is .96/28. Its next hop is going to be the VNet. It also has all those RFC 1918 summary routes too, like 10/8, 172.16, 192.168, and then they all will be pointing towards the virtual appliance, which in this scenario is going to be our spoke gateway. So let's say this spoke gateway, it's 172.30.2.4 is the IP of the Ethernet interface here, or NIC. So it will be all pointing towards .4. You will have another entry of 172.30.2.0/24, and that will also be pointing towards the .4. So this is the routing table entry of this web SG only. So now let's try to understand this routing table. When app1, VM1 wants to communicate with the VM2 in the same subnet, it's going to take a look at its routing table, and then the routing table says, okay, there isn't an entry, so it means I have to, my next hop is the VNet. Okay, it's a virtual network. So what about if I wanted to talk to .96? .96 again is the virtual network, so it means I really don't have to go anywhere else. But when I want to communicate with anything outside this .80 or 96, it could be .112, something over here. At that point, I am going to point towards this entry. And this entry is telling me to talk to the spoke gateway. So now, once the traffic comes to the spoke gateway, you need to enable your traffic inspection policy. And once traffic inspection policy is there, then we are going to send the traffic over to the transit FireNet, and transit FireNet, the same thing is going to happen, and the traffic flow is going to take the traffic over to the ILB and then the firewall and then comes back. So make sure, if this is the intent that you want the traffic between the web and the app should always be inspected, then you need to create the inspection policy. Without the inspection policy, they will communicate without going through the firewalls. So what is going to happen for the Intra-VNET communication? For Intra-VNET communication, there is absolutely no change. So the FireNet works exactly the same way as previously. So now let's talk about when you have multiple spokes. All right, so let's draw it out and let's take a look at it in Intra-VNET communication. So there is another VNet. Let's call it its spoke B. It has multiple subnets. Subnet 1, Subnet 2, Subnet 3. Let's say when this subnet, which is not part of any subnet group, when it wants to communicate with any subnet in spoke B, let's say this is the communication going on. At this time, the communication would be just fine, no issues. Now, when a subnet in a subnet group, let's say DB subnet wants to communicate with subnet 2, even this communication is allowed, okay? As long as there is no subnet group configured on spoke number B. So the third scenario could be, what about if I'm going to place all these subnets in a subnet group? And this time, app subnet group wants to communicate with this new subnet group in the spoke B like this. So that communication is also allowed here. So 3 scenarios. Now, If I go back to the Intra-VNET scenario, what is going to happen if these subnets wants to communicate, which are not part of any subnet group? They want to communicate with the subnets which are part of any subnet group, like this communication. So this communication is not allowed. So what you need to do in order to have them communicate with each other, always make sure to create some kind of default subnet group and then place them in a subnet group like this. So let's call it a default subnet group and place your subnets in that. Now, so basically the point is the subnets in a subnet group can only communicate with the subnets in a subnet group. So subnets without the subnet group cannot communicate with any subnets within a subnet group. Now, what about if there are some subnets which are not part of the subnet group? They are okay to communicate with each other. That should not be an issue. So there is one important point when you are creating these subnet groups. So you might already have some subnets that Aviatrix is going to ingest. You might have some UDRs over there. Just make sure that these UDRs are not carried over to the subnet group's routing tables. So this is one thing which you need to remember. So anytime when you convert these subnets into us or associate them to be a part of any kind of subnet group, at that point you have to go back and manually create an entry in these subnet group specific routing tables. There will be times when you wanted to add or remove the subnets part of a subnet group. Just remember that it takes about 10 to 20 seconds because of the Azure APIs. And then our recommendation is to always take a downtime or maintenance window whenever you need to make a change in the subnet group. Just remember that this Intra-VNET inspection or subnet level inspection is not going to be applicable if you have a secondary address space for your VNets. And then the architecture that I was talking about it previously, which is the dual transit FireNet, that is also not supported for Intra-VNET. All right, let's discuss the firewall health monitoring performed by the Aviatrix controller in Azure. So HTTPS is the mechanism from the load balancers to the firewalls. That's how the Azure load balancer is tracking the health of the firewalls. So the state column on the Aviatrix controller about the firewalls is basically letting you know that whether the firewall is up or not or down, which basically is the VM status, not the health of the firewalls. In order for you to check the actual health of the firewall, you need to log into the Azure portal. The way the Azure load balancer provides this kind of health monitoring, it's sending the keep alive. And if one keep alive is missed, the Azure load balancer is going to declare the firewall is down and is going to remove the firewall from its available pool. The way you can check it is go into the health probe status under monitor and metrics. Now let's discuss the load balancing and failover mechanism in Azure. So Azure ILB, as I was describing it, it provides a load balancing mechanism to all the next generation firewalls. So from Aviatrix controller perspective, we support by default the 5 tuples. And these 5 tuples basically means the source IP, source port, destination IP, destination port, and then the protocol type. For legacy application, we also provide the support for 2-tuple hashing as well. Aviatrix controller orchestrates this hashing algorithm on the Azure load balancer. So you just configure either 2 tuples or 5 tuples. As I was telling you previously as well, that Azure load balancer only sends a single probe, and then after not receiving any response, it's going to declare the firewall down at that point. So only failed firewall is going to be removed from the ILB pool. And in this scenario, it takes about 9 to 10 seconds for the failed firewall to be removed. And what about if the transit FireNet gateway goes down? So the API call is made to update the UDR to point towards the healthy gateway. And this convergence, again, depending on the Azure APIs, it could take anywhere between the 60 to 90 seconds. All right, so that's all I have for Azure FireNet. In the next session, I'll be discussing GCP FireNet. Thank you very much for watching.